Hey everybody, Dr. A here, and in this video we're going to be exploring another example of shear flow. So let's take a look at the given information. We're being told that two boards are held together by nails. If the maximum shear force the boards must sustain is 1,200 pounds, and each nail has an allowable shear strength of 190 pounds, what is the maximum spacing of the nails? So here we're given two views. We have a cross-section view where we see we have a T-shape made up of these two boards that are nailed together, okay? The top dimension of the flange is 6 inches and the thickness is 1/2 inch. And then the depth of the web is 4 inches. And again, the thickness of the web is 1/2 inch. Now, if we look at a side view, we see the same depth dimensions, 1/2 inch and 4 inch, that's we see over here. And then we see this kind of single row of nails at spacing S. And that's what we're trying to find, is that spacing S, okay? So let's go ahead and write the solution, and let's start with our governing equation. Q is equal to V times capital Q over I about the neutral axis. Now, we were directly given V, okay? That value of V was given as 1,200 pounds, all right? So the work we're going to have to do has to do with getting capital Q and I about the neutral axis. Now, we also know that the shear strength, the allowable shear strength of each of the nails is 190 pounds, okay? So here is the relationship we need to establish to get that spacing S, all right? So we're going to calculate Q, and then what we're going to do is we're going to say, hey, that spacing S is going to be the shear strength of each nail, all right? So we're going to say nail strength divided by the Q that we're calculating here. Now, how does that make sense? Well, we can establish some units here. We can say unit check, all right? So nail strength has units of force, all right? And then Q, which is shear flow, has units of force over length, all right? And so what happens when you do force divided by force over length? Well, we can say S is force divided by force over length. And what happens is the forces cancel and you're left with just length, which is the unit of spacing. So you can think of this in terms of units to help us establish this relationship, okay? And again, we know that the nail strength right here, that is the 190 pounds that we were given in the problem statement. So again, the work is really getting Q, and in particular, it's getting capital Q and moment of inertia. So let's go ahead and do that, all right? We'll start with moment of inertia, and we're looking at this T-shape right here, which we have dimensions of 6, 0.5, 4, and 0.5, all right? So I'm going to draw that here. Six, 0.5, 4, and 0.5. And I'm going to put a datum here. And in order to get moment of inertia, the first thing I need to do is get y bar, okay? And so I can say, 4 inches times 1/2 inch times 2 inches plus 1/2 inch times 6 inches times 4.25 inches. And then that's going to be divided by the total area, which should just be 5 inches squared, because again, we've got 4 times 0.5 as the area of the web here, which is 2, and then 6 times 0.5, which is the area of the flange shear, which is 3. You add those together, you get 5 square inches as your total area. So for Y bar, let's pull out our calculators and punch all this through. 4 times 0.5 times 2 plus 0.5 times 6 times 4.25. And then we're going to divide that by 5. And so I get a Y bar of 3.35 inches. So that's going to help us locate our neutral axis, which will be right here. Now, I went through this centroid calculation pretty quickly because we should be familiar with centroid from statics. If you're rusty with your centroid calculations, take a look at my centroid videos in my statics playlist, okay? Now what we need is our moment of inertia about that neutral axis, INA. So the whole reason we need Y bar is so we can then use it to get the moment of inertia, and then we can also use it to get our value of Q, that first area moment, all right? And so I'm going to break open 2 brackets here because I have 2 rectangles. So for the web, I'm going to have a BH cubed over 12 term plus an AD squared, so that's plus 2 inches squared times a distance, right? And so that distance is going to be 3.35 inches minus 2 inches squared plus, and I'm going to have a term for the flange, okay? So I'm going to have a BH cubed over 12 term for the flange plus an AD squared, so that's 3 square inches, and then times a perpendicular distance between the centroid of the flange and the overall neutral axis. That'll be 4.25 inches minus 3.35 inches. Don't forget to square that difference, and we can punch this through our calculators. 3.3. Be very careful here. It's very easy to make a mistake here. Okay. So I end up getting 6.31 inches to the 4th for this first term. And when I punch in this second term, I end up getting 2.49 inches to the 4th. So if I add these 2 together, I end up with a moment of inertia about the neutral axis total of 8.8 inches to the 4th, okay? So now what we can do is make sure that that moment of inertia value is checked off, all right? And now we're ready to get Q, the first area moment. So let's scroll down a little bit, and I've got some stuff already kind of written to help us out. So Q is equal to A prime Y prime bar. Now, if I look back at my T-shape, okay, I can use either the flange or the web as A prime. Let's go ahead and use the web as A prime just to be a little bit different from our previous example. Now, again, why am I allowed to use either one of these? Well, we have a whole nother video on how to calculate Q where we explain that, but we need A prime to be an entire area either above or below the part of the cross section that we're interested in. And what are we interested in? We're interested in this interface right here where the nails are going to be penetrating. So I'm going to call this web A prime. Now if I call that web A prime and I scroll up and look at those dimensions, that's going to be 4 inches by ½ inch. So that's going to give me 2 inches squared. What about Y prime bar? Well, I've already got it kind of labeled for us. Y prime bar is the distance in between the overall neutral axis, which is defined by Y bar, and the centroid of A prime, which is that web rectangle shape, right? So that's going to be 3.35 inches minus 2 inches, which of course is just 1.35 inches, okay? And so to calculate Q, I'm going to say 2 times 1.35, and of course I get 2.7 inches cubed. That is not a volume. That is an area moment. It's an area multiplied by a perpendicular distance, okay? So now I'm ready to start putting all this together. We know that Q is equal to, little q, of course, is equal to V times capital Q over I about the neutral axis. And so that's going to be 1,200 pounds times 2.7 inches cubed, all divided by 8.8 inches to the fourth power. And so punching this through, I get 368 pounds per inch. Now we know that the spacing required is going to be the nail strength divided by Q. And so that nail strength was 190 pounds per nail. And what we need is, what's required of us, what is being applied, I should say, is 368 pounds per inch. So we see the pounds cancel, and we get 190 divided by that 368. And so we get 0.52 inches. And I'm going to say 0.5 inches of spacing. Now, let's talk about this. Does this make sense? Well, numerically, sure. We did the calculations correctly, and, we finally get S equals 0.5 inches. I'm going to say, however, this is not very practical, okay? Why is that not very practical? Well, think about it. If you were nailing these two boards together, putting a nail every half an inch, that's a very tightly spaced nail pattern or row of nails, okay? In fact, it's so tightly spaced that you're likely to have the boards tending to split as you nail those in. Okay, so from an engineering perspective, you would probably want to design your boards such that you don't need that many nails and that tight of spacing. So maybe you need a larger cross section or a different cross section, or maybe you need to find some nails that are stronger than 190 pounds in shear capacity per nail. Or another option is not only a different geometry of your cross section, but maybe have 2 rows of nails, okay? Regardless, putting nails in every half an inch is probably not very practical. So one of the things I like about this, aspects I like about this example is it reviews and goes over the calculations, but it kind of takes us to a numerical conclusion that in practice probably doesn't make a whole lot of sense to try to execute in practice. So going back to a larger picture, you want to be an engineer, right? So part of being an engineer is thinking critically about global designs, thinking critically about, does your design or does your calculation make sense from a constructability perspective? It might make sense from a calculation perspective because at the end of the day, we're doing applied math, but does it make sense from an engineering constructability perspective, okay? And in this case, this is not very practical. But nevertheless, that's our numerical answer, and so that's the conclusion. So if you found this video helpful, please hit like and subscribe and be on the lookout for other similar content. Thanks for watching.